Right, and there's one last thing to talk about in this section, which I'm going to talk about graphically, because I think this graph contains everything that you need. Okay, it's very dense, but it contains everything you need. So this would be the graph, the titration curve of a weak acid and a strong base, a strong alkali. Okay? So when you start adding a strong alkali to a weak acid. Okay, this could be ethanoic acid. We start adding it. Obviously, the end point here is at 25 centimeter cubed. But when we first start adding, what does the weak acid do? Well, it reacts with the alkali to produce a salt of the weak acid. So you'll have HA and NaA, a weak acid and the salt of a weak acid. What is a weak acid and the salt of a weak acid? It is a buffer solution. So what happens is we start adding the sodium hydroxide, the pH starts to go up, then a buffer solution is formed. And a buffer solution, what does it do? It resists changes in pH. So this curve flattens off and then moves slowly across towards the end point. When it gets to the end point, obviously, strong alkali causes the pH to rapidly increase between about 6 and 11, just over 11, and then it levels off again. Okay. Remember, if we wanted to use this reaction as a titration, we'd have to use an indicator with the working range that coincided with this. So phenolphthalein was our favorite, wasn't it? Great. And then typically in exam questions, they ask you to draw this curve and show where it ends. So you'd have to know the pH of the alkali when it's in excess. I don't know if you remember, but the pH of 0.1 molar sodium hydroxide was 13. So this should go towards 13. You can also work out the pH that the acid started at before you start adding sodium hydroxide. That's a classic example of an exam question. So you're given a Ka, so they might ask you to work out the pH at the beginning. So that might be one of the marks. But the shape here goes up, flattens off, and then it curves up, goes directly up from about 6 to about 11 or 12, and then goes across. That's called the buffer region or the buffer zone. And this point here is very important. Okay, this point is at 12.5 in this case. It's halfway to 25, 12.5. And what happens there is at 12.5, you've got, if you think back to the equation or the expression for Ka, at that point, the acid concentration and the ion concentration, so the HA and the A minus, or if it was ethanoate ions, it would be the ethanoic acid and ethanoate ion concentrations are equal. And because they're equal, they cancel. Look back at the expression. So if they cancel, that we're left with Ka equals hydrogen ion concentration. So pKa would be equal to pH because both of them are minus log to the base 10. Have a think about that, see if you can do the maths. It's not that bad. It looks impressive, but it's not. Now, this point is called the half equivalence point and can be very useful. If you know the end point and you can add half that amount and find the pH, then you can find the Ka for the acid, which can be useful. Okay, you can get a little bit more information about that by reading the pages from the textbook. There are no questions, but it just explains the production of that particular equation in a bit more detail. Okay, to finish off this section on weak acids, buffers, etc., enthalpy of neutralization pops up, and we've seen this before, remember, the enthalpy change, the energy change when 1 mole of water is formed from 1 mole of aqueous oxonium ions and 1 mole of aqueous hydroxide ions. Okay, so that for a fully ionized strong alkali and strong acid, then delta H of neutralization, the enthalpy of neutralization is minus 57 kilojoules per mole. You could say here per mole of water produced. Now, when you've got a weak acid or a weak base, the energy required to break the bonds in the weak acid or base can cause this figure to be less exothermic. So let's take this reaction. We've got the reaction between ethanoic acid and a strong alkali, could be sodium hydroxide, potassium hydroxide, producing ethanoate ions and water. So it's just acid plus base, salt plus water. However, for the ethanoate ion to react, we could say that we have to break the OH bond to produce hydrogen ions that can then react with the hydroxide ions to produce the water. Now, in this particular Hess cycle, because that's what it is, we know that delta H of neutralization is minus 57, and we can find out by experiment that the delta H for this reaction is minus 55.2 kilojoules per mole. So what does that tell us? That tells us that it takes a certain amount of energy to break the bonds, the OH bonds. And we can use this Hess cycle, this Hess diagram, to work out what delta H1 actually is. Using Hess's law, this reaction, minus 55.2, would be equal to delta H1 would be equal to, so this reaction here, this delta H minus 55.2, and then we've got to go against this particular arrow, so it's minus 57, and that works out to be plus 1.8 kilojoules per mole. So that tells me how much energy I require to break the bonds in the OH of this ethanoic acid molecule. Okay, so it's this is this minus this, plus 1.8 kilojoules per mole. Now, just as an extra point here, obviously, when you produce ions, then the ions are hydrated. So even though it takes energy to ionize this weak acid, even though it takes energy to break that bond, obviously the energy is recovered when ions that are produced are hydrated by water molecules. When ions are hydrated, it's an exothermic process. Okay, so the enthalpy of hydration of some acids and bases is sometimes greater, means more exothermic than minus 57, precisely because of this. If you look at, for example, the reactions between nitric acid and barium hydroxide, then you get more energy released when they react. And it's to do with the hydration enthalpies. Essentially, because in these reactions, different ions are formed, then what happens is they can be hydrated to different extents and more or less energy can be released. Okay, you can see with the weak acid, for example, weak acid and strong alkali, it's less than minus 57. With a strong acid and a weak alkali, again, it's less than minus 57. This is strong and strong. Barium hydroxide is relatively strong, but when it reacts to produce water molecules here, then the barium ions and the nitrate ions, obviously, they give out energy. They're hydrated more efficiently and they give out energy. Right, have a look at the questions indicated in the textbook and read the pages just to make sure that we've covered all of the material, and then you're ready for the exam style questions at the end of the chapter.